Well, good morning, everybody. The last full week for us. I found a graphic. I couldn't find a graphic that I was super excited about. So anyway, this one I thought was, good morning, Vince. Morning, Brooksy. Who else is out there? Good morning, Jack. Good morning, Dice K. So glad you guys are all still sticking it out. This week I'm feeling a lot better than I was last week because we've almost gotten ourselves there. So, and also it's pretty amazing really that everybody who sent the lab, which was everybody but 2 people, sent something that worked just like it was supposed to. So that's really amazing. So that was a good job. Anyway, so there's my graphic. For us to keep calm and you guys keep up the good work because it's we're going to be online in the fall and I'm not going to be doing this hardware stuff. So yours is probably the last class that we'll ever get to do what I consider to be sort of the sexy assembly course with the hardware and the ARM processor. So in the fall they're just going to be back on the old Intel processor and it's not going to be nearly as much fun. But I don't know how we would do the hardware and the circuits all semester without any face-to-face time. So anyway, good job. Thank you for that. I'm going to do some bookkeeping to start. So let me bring up my browser just to make some notes about the dates. So the last date of the semester, meaning I'm no longer on contract, is May 29th. So Friday, May 29th is the last day of the semester that I'm paid to work. This is not going to affect you guys unless you are running late labs. So mostly I'm saying this for people who need to get some late labs submitted. I am off contract after Friday, May 29th. So if you want something graded, I need to get it by May 29th at the latest. For those of you who've been keeping up, probably at the right after we stop our meeting on Tuesday next week, you'll just submit the last little review assignment and you will be done. But for those of you out there in the world who are watching this video later and you're behind on things, just know May 29th. May 29th. Okay. So what I've got here is the home page. We're not going to do this work in class, so normally I would take some of our extra time and do this, but I wanted to just show you that it's there. One thing that we're not going to talk about this semester is how do you do floating point numbers in binary. And sometimes I have an assignment for that, and sometimes I don't. So this semester we're not going to do a floating point assignment, but I have posted here a short assignment with some links to readings about how do you do floating point values in binary, and I've also posted the associated answer key. So if you personally are interested in knowing how floating point works, you can do this short assignment and do a couple of the readings and then look at my answer key. I will at least sort of give you some sense of how floating point works in binary. So that's new. And then on the schedule, the other thing that's been changed, so we're going to do homework 15 today, and then since it's short, I think we can at least get a start on the last lab and then finish the last lab this Thursday. Most of you are probably on Thursday gonna submit the last lab, and it will be complete and you will be done with labs, and then we'll do a review next week. But just to be generous to people, I'm leaving. I'm still accepting the final lab without any late penalty next week as well. Okay, but anyway, I did put these dates here as well, May 29th. And again, there's a few people who are running behind on labs, and none of you guys who are here all the time, but some of the video people are probably running behind on labs. Just note nothing after May 29th, because at that point, they're no longer paying me to work. until sometime in late August again. Okay, so homework 15. I'm going to check in with chat. Hopefully I greeted everyone who's here. I did, I believe. Oh, I see Kevin's here, so good morning, Kevin. Give a shout out to everybody in chat if you feel like it. All right, so homework 15. This stuff is going to feel a little bit like it's hard to put the pieces together in your head just sort of looking at these words. So I'll do my best to explain to you what's going on. But let's get the answers, and as we get the answers, we'll do our best to discuss what the stuff means. Okay, so the setup here is that we are talking about interrupts, and interrupts are hardware or software generated events. We often call them events that the processor has to stop and deal with. So we know some hardware examples are things like clicking a mouse. That is an event that the processor needs to go, sometimes at least, deal with the fact that the mouse was clicked. Maybe that means that a window has to be closed, or a character in a video game has to move. Pressing a key on the keyboard can also cause an interrupt. That's an event, so that's input, and the processor sometimes has to stop and deal with that event. There's also software interrupts, and the easiest to understand example of a software interrupt is divide by zero. So that is a software caused error that the processor has to stop what it's doing and deal with that. And then if you've done programming algorithms too, then you've probably dealt with exceptions. And when we throw or try and catch exceptions, those are all software interrupt associated activities. So that's what we're talking about, is these sort of special events that the processor has to stop and deal with, and then how do you do that in ARM? Okay, so I'm just going to do what I normally do, which is bring up the reading, and we'll go hunt down some words that read good. So the first question is, what is an interrupt service routine? The first link says interrupt handler, and I usually put these in order, but the reason I called it interrupt handler is because that's the title on Wikipedia. But if you start reading, you immediately realize that an interrupt handler is another way of saying an interrupt service routine. So I'm going to read and then grab. So in computer systems programming, an interrupt handler, also known as an interrupt service routine, or ISR, is a special block of code associated with a specific interrupt condition. Let's see, do we want to get more than that? I think we do. Interrupt handlers are initiated by hardware interrupt, software interrupt instructions, or software exceptions. I think I like all the way down to exceptions right here. I'm going to grab that whole thing, stopping after exceptions, because that extra stuff about device drivers doesn't interest me. But I like the words that precede that. And then I'll replace that. I'll put a period there at the end instead of a comma, just to clean it up. So in computer systems programming, an interrupt handler, also known as an interrupt service routine, is a special block of code associated with a specific interrupt condition. When they say block of code, you can sort of just think of, good morning, Dylan. Sorry I missed you there. I still didn't get Kevin to chat. Good morning, but good morning, everybody. Okay, so when it says block of code, you can sort of think in your high-level programming mind, a block of code, it looks like a function. And you can also sort of think that a routine makes you think of a function. So in assembly, of course, we don't really have functions per se. We just have sections of code that are grouped together like macros. So anyway, an interrupt service routine is simply a block of code that handles a specific interrupt. So, they clicked button number 1. That goes to a particular interrupt service routine. They clicked button number 2. That goes maybe to a different interrupt service routine. Okay. interrupt vector table. So interrupt service routine, probably people get that better than interrupt vector table. So let's bring up that link. The words are fairly easy to understand, but then making sense of what it means might be harder. So an interrupt vector table is a data structure that associates a list of interrupt handlers with a list of interrupt requests in a table of interrupt vectors. Now, I think the words "in a table of" just make it a messier answer. But I'm going to go ahead and grab that and maybe clean it up. I also like this sentence. So each entry of the interrupt vector table, called an interrupt vector, is the address of an interrupt handler. So I'm going to grab those first two sentences and then maybe strip out some words that I don't like. All right, so an interrupt vector table is a data structure that associates a list of interrupt handlers with a list of interrupt requests. These words, I think, make it more confusing, so I'm just going to say interrupt request, period. Each entry of the interrupt vector table, called an interrupt vector, is the address of an interrupt handler. So what the hey does that mean? So I mean, you could sort of just think about any table of data. In fact, let's look at the code. Let me just show you the code for it and show you what it looks like in ARM assembly code. Should be in main. Okay, so here's the table in ARM code right here. So what this table does basically, and it's easier in my opinion to think of this as pointers, which is really what they are. They're just addresses. So the table is pre-configured in ARM. So meaning the first entry of the ARM vector table, which is why that's called vtable. The first entry in the ARM vector table has the address of the stack. What do I want to call it? Initializer. It's a pointer to a particular routine. So every entry in this table is, the order of the table is pre-configured in ARM, and then where each entry in the table points to, the programmer handles. So the second entry is a pointer to the block of code that you want to engage when the reset button is pressed. So what I've done here is I've put an address, and if we go down, we'll see here's reset handler. So I've mapped into this table the second entry, which is where the reset pointer goes, to a specific interrupt service routine or interrupt handler. I don't know if that makes sense. So the third entry is for whatever NMI is, but I have made that a null pointer, meaning I have no service routine to handle that kind of interrupt. And if you look down, the hard fault entry is null, the mem manage entry is null, the bus fault entry is null, the usage fault entry is null, and these are all pre-configured. The order of these is pre-configured in the ARM processor, and my job as the programmer is to connect the interrupts of interest to handlers that I've written. So we have to go all the way down this table, all these null pointers until we get to this interrupt, which I have mapped not to a null pointer but to a particular interrupt service routine, which again is just a block of code. And you can scroll down and here's the pin 0 handler. So I've mapped that interrupt to this handler, and then I've mapped the interrupt that follows it to this handler. There are more interrupts after that, but I really just needed to know all of these out so I could actually get to the specific ones that I want, because you can't leave holes. So I don't know if that helps or not, but this is what the interrupt vector table looks like in ARM. And you can see that we have mapped 4 of the interrupts to handlers. And then all of the rest of these don't have a handler that we've programmed in. They're just null pointers. All right, so that's what it looks like in code. What do I want to do? Oh, put the browser back. Okay, so that's an interrupt vector table. That's a data structure, a table that associates interrupt handlers, which are the order of them is pre-configured in ARM, with the list of interrupt requests, which for us is mostly null, but in a couple of cases we've actually mapped the interrupt handler to a specific block of code. Okay, so now we'll move on to number 3. There's only 5 here, so let's go NVIC on ARM. This one's a little bit more intimidating to find the answer. So ARM calls theirs the nested vector interrupt controller. That's just ARM terminology for their interrupt vector table. So this is simply ARM terminology for IVT. But let's go to this reading. This one is pretty intimidating, so you should do this kind of thing. Keyword it. I'm going to look for nested because I'm looking for nested vector interrupt table in here. Okay, so I found the word nested. So words, exceptions include reset, software interrupts, hardware interrupts. All right, so I recognize those kinds of things. Interrupts on the Cortex-M are controlled by the nested vector interrupt controller. I like those words, so I like this sentence. That's the second sentence, or that's the third. But anyway, each exception has an associated 32-bit vector. And a vector, remember in this case, is really just a pointer to something. A 32-bit vector that points to the memory location where the interrupt service routine that handles the exception is located. So I'm going to grab interrupts through located. Actually, I like this ROM one too. Vectors are stored in ROM at the beginning of memory. I like that next sentence too. I'll linger on this one so that you can see what words I took. So all we're really doing is restating the same damn answer for ARM terminology specifically. So the nested vector interrupt controller is the interrupt vector table on ARM. That just happens to be what they call it. So the NVIC controls interrupts. Each exception, but we can think of that as an interrupt. So each exception has an associated 32-bit vector, which is really just a pointer. But it even says that, right? That points to the memory location where the interrupt service routine that handles the exception is located. I'll go back to the ARM code and just remind you what the heck this means. Vectors are stored in ROM at the beginning of memory. Now the reason I took that piece is ROM is read-only memory, and the reason I took that sentence, vectors are stored in ROM, is to tell you that the nested vector interrupt controller is pre-configured in the ARM processor. It's already there, the entries are already in a particular order, and your job as an ARM assembly programmer is simply to put the vectors, the pointers. So if I'm interested in this exception or interrupt, what handler does it go to? Right? So that's the reason why we picked up the ROM sentence, is just to remind ourselves that in ARM, this table is pre-configured. It's in a particular order. And the only thing that you control as the programmer is where the interrupt service routines are. So now I'll go back and I'll just look at that same stuff just to try to drive the point home in software, and then I'll bring that answer back. All right, so here we are. So how do I know that those are in that specific order? Because this is built into ROM, meaning it's built into read-only memory. I cannot change the configuration of this table or the order of its entries. The NMI controller, whatever that is the third entry. And that's because it's in ROM, I can't change that it's the third entry. It will always be the third entry. The only thing I can change is where the interrupt service routine goes. Now in this case, I don't care. I don't even know what NMI is. I don't care about that interrupt, so I just null out that pointer. So that vector or pointer points nowhere, meaning there is no special code in my program to handle that interrupt. There's no handler in my code to handle the hard fault interrupt. And then all of these until we get down to these two interrupts, which I do care about. So I have mapped those to interrupt handlers or interrupt service routines that I have programmed, written in my code. So I don't know if that helps. Hopefully it helps a little bit to kind of get this. Doesn't really matter tons, but since we're doing ARM and it's a cool feature of ARM, you should know of it. Okay, number 4. So this is just to have you look at some documentation a little bit. The hexadecimal addresses of the reset handler and the UART0 handler. Remember, because these are pre-configured in ROM, the addresses where these go are always the same. Now, the interrupt service routines that they map to can be changed by the programmer, but where they are in the table never changes. So reset handler and UART0 handler. That should be in the same chapter. Hopefully you can see. Okay, you still can. So let's go look for that. If we scroll just a little bit down in this NVIC section, we will see, if we look through, here's top of the stack, sounds familiar. Reset handler, if you notice in our code, by the way, eStack, reset handler. So here's the address of reset handler. And again, that's just a reminder that these are pre-configured in the ARM processor. You can't change where the reset handler goes in the table. It's the second entry, and this is its address, which you notice, by the way, is 4 bytes greater than the first address. So each of these addresses is 4 bytes or 32 bits. So anyway, there's the address of the reset handler. So I'm going to copy that and go put that in. Reset handler is that. The UART0 handler, I gotta go get. If I scroll down, so usage fault, SV call, GPIO, here's UART0 right here. So that many bytes out. I think I just picked that one at random just to have you look through there. So again, those are addresses in that table. So where in the table the reset handler vector goes never changes, but where you point it to is what you change as a programmer. More or less, you write yourself a function for this, and then you tell the table that's where you go on this interrupt. Chat. Okay. And then let's get, I made that not what I want. Okay, this is what okay, so last one is BX and LR instructions, and then this invocation. So let's do the same thing. Let's go look at BX. So BX instruction branches to the specified destination containing an ARM or a thumb instruction and optionally executes it. Okay, so that's a little bit different because what we've used for branching so far is just branch to address. So this is branch and execute. It's not really what it means, but we can kind of interpret it that way, that BX means to branch to a location and then at least optionally begin executing code there. So I'm going to grab that sentence. That's the BX part. So the BX instruction branches to the specified destination. I should probably put the signature of it, right? BX dest. So let's put the signature of it, and then it makes sense when we say what do you mean by dest? Oh, it's the. So anyway, you branch and then optionally execute at a destination. Okay, let's go look at LR. Check in chat to make sure you guys are doing okay. LR. So link register. So LR stands for link register. It's a special purpose register which holds the address to return to when a function call completes. More or less, this is what it means in ARM. So let's just take that. Link register, and then I'm going to put LR in my answer because it asked me about LR. So it's a register, and it's a special purpose register that holds return addresses. So you can imagine, hopefully, that you branch to a location, you execute some code, and then the link register takes you back to where you came from. That's kind of how this works. So you branch to a location, you execute some code, and then the link register allows you to return to where you left off. And we can actually see this in our circuit. I'll run it and I'll show you where that's happening. All right, so BXLR itself, this may not explain. Let's see if I go back to this chapter 12 interrupts, if we can find BX in here. That's pretty good. There's some extra words in here that are confusing. The top 24 bits, which whatever that means, or that means. So I like that. That's mostly what we need, isn't it? Part 3. So we return from an interrupt. The interrupt service routine executes the typical function return BXLR. So in ARM, this is how interrupt service routines let the program get back to where it left off. We're going to go look at that. Let me save this for myself. I don't remember if I have this. So just in case, I'm going to go grab it for myself. This is homework 15. Okay. So BXLR is a function return, if you want to think about it that way, on ARM processors. So let's go look at this in code. Okay, so some of these are really hard to see in code, but you sort of just have to, unless we were doing a much longer course. This interrupt we have wired to one of our buttons. So this particular interrupt in the nested vector interrupt controller on the ARM processor, we've actually wired it up to a button, and then in software we've connected it by this pointer to a specific interrupt service routine. So when one of the buttons is pressed, it causes a hardware interrupt on the processor. The processor, knowing which hardware interrupt it is, goes into its table and then immediately branches to the location where the interrupt service routine exists. If it's null, then nothing happens. But if it's not null, then it goes there. So in this case, it's going to go to pin 0 handler. Here it is. And pin 0 handler then executes code in response to that interrupt. Now in our case, there's a little bit of code that I left behind just to clean up the interrupt, but then we have a call to a macro. So in our case, basically, pin 0 handler, what it does is it increments a variable. That's it. It doesn't change the display. It just increments a variable. And then notice it branches to link register. So what this really does is once the interrupt service routine is done, ARM knows where it left off, and it will automatically go to where it left off when it came to do this interrupt, and it will branch back there and continue where it left off. So you kind of get that for free. If you BXLR, ARM remembers how it got here, and it will just automatically use the link register to go back to where it left off. You could see this in our circuit, by the way. So I'm going to power up my circuit. You can see it. Yes, you can. Let me power up my circuit and just show you. Because if you understand this, then it makes the circuit make sense. Okay, so this thing starts out in mode 0, I guess. It's just cycling through an array and printing out the values. Now when I click one of the buttons, and I can't remember which it is, but when I click one of the buttons, it causes an interrupt. And what the interrupt does is it goes to this interrupt service routine. It increments or decrements a variable, and then the BXLR instruction actually brings it back to where it left off. So the weird thing, the reason why it looks like there's a lag in the mode light changing is because after the interrupt service routine, which only increments the mode, it goes back to where it left off and continues to print the remainder of the array, and then it does some updating of the display. So if I click, I don't remember which button it is. Okay, it wasn't that button. Oh, there it goes. So what happened is it did increment the mode, but then it came back to where the BXLR brought it back into the middle of the array, and it had to finish printing the array before other instructions kicked in to change the display. So right now the logic is quick because it doesn't have any work to do. So I'm going to click the button. It will increment the mode and then branch back to where it left off. And so now it's decrementing the mode and branching back to where it left off. This piece is off. Oh, there it goes. Anyway, so the reason why there's a lag is simply because the BXLR actually goes back to where it left off and then has to finish the next bit before the display code comes into play and gets executed. Okay, so, but anyway, it's not huge parts of the takeaways of this course. So if you got that's great. If you got it a little bit, that's good as well. Hopefully you did get it at least a little bit. Okay, so I'm going to show you what I've got set up, and then I'm going to switch modes here, as it were. Okay, so that's the end of the homework. I'm going to sit here for a minute or so and see if there's any questions about the homework. Then I'm going to take a short break and come back and start working on the final lab. So while I'm taking a break, there's a chance for you to get the, if you haven't already, download the final lab files. I have them all right here. Config we won't have to touch. Macros we will. It looks like most of it's been given to us for free, so thank goodness for that. Anyway, so I'm going to take a break. I'm going to get myself some water, and that hopefully will give you a couple of minutes to, if you haven't already done it, download this code, and then we will work some of these problems for the last 20 minutes or so and get ourselves a start. Populate array. Yeah, I'll just redo that. It's fine. Increment mode, decrement mode. Compute min, max. Where's average? Display array. Oh, there's average. Okay. So hopefully everyone got that. No questions came through in chat, so I'm going to go get some water, give you a couple minutes to download this code, and then we're going to start working on the final lab, because our goal will be to finish the final lab. Start it today, finish it on Thursday, and then we just have sort of review on Tuesday next week, and then we'll be done. So I will be right back with some water. Okay. So let's knock a little bit of this lab out. So like I always do, I'll start in main and just work my way down in main, implementing things as we go. So I notice here, we'll just sort of study this code as we go. We notice that there's a lot more variables this time. We're used to the mode variable. The seed variable we're not actually going to use. I just couldn't get that to reliably work for people. But the garbage is still left, so you're not going to see seed come into play anywhere. The offset is being used by parts of the macros that I've written for us. Max and min, so those are going to be variables that we will use to compute and then store the maximum and minimum values in the array. We could hard code those values, of course, but the fun is seeing how to develop these algorithms in assembly. Same for average, so we'll have a macro that computes that. And then we have an array counter, which is not counting the number of bytes, but counting purely the number of elements, which some of my macros use. And then we have the array itself, a 40-byte zeroed out array called numbers. So there's a couple of new variables in there, which we'll keep track of. These are for the compiler phases that those are there, so we don't have to worry about those. You've seen all this mess before. All of these registers are kind of the familiar ones, the clock, the A stuff, including the buttons, the B stuff for LEDs, the C stuff for LED, and then all this other mess down here. There's even some when I was doing some random numbers, which I don't want, but that's okay. These are all about the interrupt handling, so it's confusing and difficult to do, but you can see there's some NVIC things. All of this stuff could actually be taken out, but let's not mess with it. Okay, anyway, so that's just all memory banks on the processor. All that's been done for us. Here's the nested vector interrupt table, which has been set up for us. It's got 4 interrupt service routines that it refers to. Here's the reset handler part. Here's pin 1 handler, pin 0 handler, which is already set up. Here's pin 1 handler, which is already set up. I'm just looking for the numbered elements. Comment in, test populate. We're not going to do that. Let's just skip that. This has got like stuff that I don't care about. We're not going to do any of that stuff. So let's just leave 1 and 2 alone. I may update that for people who come in later, but we're not going to touch any of that. So it's already calling these macros for me. So do I actually have anything to do in main? I do not. There's nothing to do in main. So if you're watching the video later, we're not doing any of this stuff. So I'm just going to say skip 1, skip 2. We don't need that stuff. So main is already set up. We just have to write macros in this case. So here's one of the macros, compute max. That'll be the first one we do. Actually, we should probably do the reset handler stuff like increment and decrement mode. Compute max, compute min. Those are going to be pretty similar. Compute average. We'll probably for sure do that one on Thursday. Anyway, I'm just pointing out here in main, there's nothing to do. We're going to skip items 1 and 2 and just focus in on these compute macros. Hopefully that doesn't mess anybody up. Skip 1 and 2 in main, and then let's go to macros and let's do work there. I've had to switch to a mouse, so you're seeing me struggle a little bit because the external mouse is very uncomfortable, but my cheap laptop is not liking the beating I'm put on it with the number of hours I'm spending at it right now. Okay, so let's just work our way down. Or do we want to do, yeah, let's do the old stuff first. Let's do these first. We've done decrement, increment, and populate array, so I'm going to redo those before we go to the new stuff. And then there's nothing new below line 30, I think. This is all already done. Yeah, it's all already done. So everything we need to do is the macros above line 30. So same old code here. We're going to populate the array. Remember, when I write macros, if I put underscore var, that means it's not a register and it's not a literal value. It's coming in from memory, and that changes the way that we load it up. So the first thing to do is to get the address of that thing. The backslash is because that's how you access a macro parameter. And then the equal sign is because we need the address of that macro parameter. Some people had problems with like little spacings and stuff, which might break things. So just be careful about what you're doing. So now we have the address of that array variable in R0. We're going to get, well, that's all we need for that, right? And now we just start going. And then I like to do the pushes and pops at the end after I know which registers I'm going to use. So let's see, I'm going to move into R1 the value 5. And the reason I'm doing this is because you can't store a hard-coded value. You have to, stores have to be written with registers, so I cannot do a 5 here. I get a compiler error. So I have to use a move to get that 5 into R1 first, and then I can store the R1 into the array. And just for clarity's sake, I'm going to do 0 bytes of offset. So that's the 5 going into the first position of the array. And then I'm just going to repeat that a whole bunch of times, of course. So the second value I'm supposed to do is 7. Store that into R0, but move over 4 bytes to clear past the first one. 3 is next. Store that in the array, but now I need to move 8 bytes over to clear past the first 2. Someone sees me making a mistake, don't hesitate to put it in chat. 0, 12. If you want to, you could copy and paste this from last week's lab. It's the same code. What's now? 1 is next. That's 16 bytes over. And there are, of course, other ways to do this. I just thought this is one of the easier ways for people to understand how to do it. 20 bytes over. 2. 24 bytes over. 8. 28 bytes over. 32 bytes over. 6. 36 bytes over. So there was a version of this a few semesters ago where we did random numbers, but the amount of extra code to get random numbers to work was so giant that we just got rid of that and kind of just made a scramble of numbers so that the algorithms could do their work. And also, of course, if you're using random numbers, it's exceedingly difficult to test your code because you don't, when they're random, you don't know what the result should be. So it's important to put these numbers in order because when I test your code, I'm going to be looking for particular results, right? Like the average should compute to something and the minimum and the max should compute to particular things. And then also the way the array displays the values in this order, right? That needs to be predictable. So anyway, please put them in that order and use those values. That way it's easier for me to test when I look at your stuff. Last step here is to push and pop. So I used R0 and R1. So I'm going to push those and then pop those at the end. And then I'm going to go hit this with the compiler. So I'm going to write a macro and then compile a macro. And just kind of toggle back and forth. So, oops, it's going to be messy. Bad instruction. All right, so it looks like I got to do a little bit of cleanup. Get seed on line 148 in main. I don't like that. Okay, getting rid of that crud. So I'll give you a chance to catch up, but I just had to go back in and comment a piece of code out since I eliminated the random number part and forgot to clean up a little bit around it. So in main, please, you're going to get an error, get seed, comment that out. Skipping those elements 1 and 2. And then go back and compile. All right, so I'm all good. I'll wait for a second and see if anyone has any problems. But if you're getting a compiler error, let's fix it now before you go any deeper. Hopefully that means everyone is doing okay. So let's just keep it compiling. In other words, just do a little bit and then compile. Okay, so there is... anyway, if you're watching the video later, be careful about these things in main. We skipped a couple of things, so and then I had to comment out this get seed line. That's part of a random number version of this that I've decided to scrap for now. Okay, thank you, Jack. Okay, so there is populate array. We've done increment mode and decrement mode before, so I'm just going to actually work my way up. So increment mode. Same thing here, it says mode underscore var, and I know that in my assembly code, when I put underscore var, that means something in memory, which means that I have to get its address of that parameter. So the backslash is because that's how you access the parameter in our assembler, and then the equals is how I get the address of it in memory. So R0. So next thing to do is to get its value. So dereference the pointer, get its value. We don't want to go above 3. So this is increment. So the way we did this before is we looked at that value and we said compare that to 3, and then if it is lower than 3, we can add, if it's lower than 3, 1 to it. And let me space those out so they look a little nicer. All right, so we compare R1 and 3. If it is lower than 3, it is safe to add 1 to it, increment it when it's lower than 3. Then we store it back. So put it back into memory, and then we're done other than the pushes and the pops. So this will only increment R1 when it is lower than 3. So if once it reaches 3, it won't be lower than 3 and it won't increment it anymore. Let's see, we need to push R0 and R1. I did something wrong here. Doubles. 0 or 1. And pop R0 and R1. And then let's go hit it with the compiler and make sure that it's still working. So my laptop, I like it. It's a Linux laptop, but one of the mouse buttons is about to fall off. The delete key keeps falling off. Half of the speakers don't work anymore. It's a poor thing. It's just taking a beating. All right, so I'm still compiling. Hopefully you are too. This is all sort of, you're seeing obviously logic. So if it's less than 3, increment it, that kind of stuff. The load store parts. Anyway, hopefully that worked for everybody. It's the same increment mode as last week. So if you wanted, you could just copy and paste that. Trying to go at a decent pace and not too fast and not too slow. So now I'm going to move up to decrement mode. If at some point you get a compiler hiccup, please say so in chat, so we'll stop and make sure that your stuff's still working good. Decrement mode, so same idea. I need to get the address of that mode variable, which I know is in memory, which is why I need the address of it. I know it's in memory because Boyd, puts _var when they're in memory. Dereference that pointer and get its current value, and then same thing but the other direction. So now we're decrementing, so we're going to compare it with 0, and as long as it is higher than 0, it is safe to subtract from it. And then I just move these over a little bit to make them line up nice. So compare R1 is 0. As long as it is higher than 0, it is okay to subtract when it's higher than 0, 1. And then I'll store that back into memory. And then I used R0 and R1, so I'll use the stack to preserve those and restore them around my code. And hit it with the compiler just to make sure it's still compiling. And then I think we had time, we'll attack one of these. Problems. And again, I'll wait. I'm just going to hit pause for a minute or so and see if there's any compiler issues. All right, that's good news. So Dylan's good to go. Hopefully everyone else is too. And I just go sort of waiting for one of you. One of you saying you're good to go, then sort of fingers crossed that other people are. But if you're racing to catch up, you can also let me know, like just give me a sec or something like that. I don't think anyone's going to mind. Okay, so now we get to do one of the more interesting ones. So let's do, we'll go back up and do compute minimum up here. Now you've seen this algorithm that I'm going to use. I'm going to get the first element of the array. And then I'm going to compare it against, so I'm going to assume that the first element of the array is the minimum value, and then I'm going to look at the remaining values, and if I find one that's lower than the first one, then I will use that one as the minimum. You've done this algorithm before, basically, so something like this, so minimum equals array at index 0, and then you have like a for I equals 1, I less than the length. This is pseudocode. I'm just kind of showing you what we're doing. So there's the whole algorithm. That we're going to do, just so you know what it looks like. That's our algorithm, mostly. We're going to cheat in one part of it. But anyway, that's the algorithm that we're about to write to compute minimum. Hopefully we get to where that's compiling, and then we will call it a day after we test the circuit a little bit. Okay. So here we go. We have a whole bunch of variables. We have an array variable, an array length variable, an offset variable, and a min variable. So that's a little bit scary, but let's just pick off one piece at a time. And then I happen to know, because I wrote it, that we have some macros down here that may help us. So I'm going to review them and see if what I want is still here. Show our increment offset. That could be handy. Reset offset, that could be handy. Increment offset, reset offset. Okay, so here we go. Minimum, right? Yeah, okay, minimum. Okay, so let's start by getting the address of that array variable. So this array variable right here will get its address. 1 or 0. So that line right there is array at 0. That's the code that does that. So we're going to use R1 as temporarily our minimum value. So what we're saying here is R1, which is going to represent our minimum value, is equal to, we've loaded the value from the array at position 0. Okay, so now we're going to do this loop. So we have this I equals 1. We actually have a macro that does that. I could have put this at 1, couldn't I have? Why didn't I put it at 1? I should have. So here's the I equals 1. I'll go down and show you the macro here in a second, but that's our, I need to use this mouse. That's our I equals 1. We're going to use a macro to do that. So I have to do a backslash on that offset variable in this macro to share it with another macro. So let's go down and just make sure that that macro actually does what we think it is, which is to take this variable and set it to be 1. Reset, 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 way the hay down here. Reset, reset, offset. So give it the offset, an offset variable and a value, and it, yeah. So notice what it does is it gets the address of the offset variable, it gets the value into a register, and then it stores that value back into that offset variable. So that is basically our I equals 1. Check and chat just to make sure we're doing okay. So that's I equals 1. Now I just happen to know this because I've thought through it, but here's the for loop. So I don't want to repeat the reset. So in a high level language, of course, that first piece is never repeated, but in low level, it would be if it's in my loop. So I reset I to 1 before I enter my loop. And by loop, I mean I'm going to use a label that I branch to. Okay, so this is a little bit weird because this is assembly style. I'm going to have to write 2 lines of code to be able to access the offset variable. Just unfortunately, this is the way that it has to be done. I don't know of a way to avoid it. So those 2 lines sort of give me my I to work with. But I need it in a register. I can't write the code that comes after it. Okay, so those 2 lines of code is just putting the value of I where I can use it in assembly. So R3 is I. But I have to do 2 lines of code to get to that. I have to basically get the address of the offset, the counter, and then I dereference the address to get the value. So R3 is I. That's what those 2 lines mean. R3 is I. All right, this one's going to look funny. You've done this once before. So that line with that funky logical shift left 2, you may remember that I messed that up and put a 4 last week. So what I've done here is I'm going into the array, which is R0. This is my index. That's my I. And this is my scaling factor. If you left shift by 2, you actually scale by 4. So this whole code is accessing the array. The array is R0. The index is R3, that's the I. The LSL just scales to the appropriate number of bytes. And LSL2 scales to 4 bytes. So that's accessing the next element of the array and putting it into R4. So what I wrote in the note there is now we have R4 being the array at index I. That's a lot of work just to get the array at index I. No doubt you knew that. But now we do a compare R4 with R1. Because we want to know, is that latest value I pulled from the array less than what I think is currently the minimum value? So that's my if statement. We're using unsigned, so we're just going to know that we're using unsigned. So if R4 is lower than R1, R4 is lower than R1, then we replace R1 with that R4. Hopefully that makes some kind of sense. I'm going to change the wording here. So if R4 is less than R1, then R1 is R4. It's the same algorithm. Hopefully that you can track that. So there is our I equals 1. We do a get array at I into R4. Then if R4 is less than R1, then R1 is R4. Now we're going to use another, be careful here, we're going to increment the offset, but we have a macro to do that because it's a pain in the butt to do. So let's use the macro. We're going to increment the offset. We're going to share the offset variable that we have here, and we want to increment it by 1. In other words, add 1 to it. So this is I++. If we want to, I'm going to say that, but if we want to, we can I'll go look at increment offset, not mode, increment offset. Here's increment offset right here. So it takes a variable and an amount to increment by. So there it gets the address, gets the value, uses a middleman for the amount, and then it adds that amount and then stores it back. So that's what it does. But anyway, I used it to pull off an I++. The reason I wrote the reset offset and increment offset macros is just so there wouldn't be so much code in here. We could just focus on the algorithm. So there's my I++. Now more pain, unfortunately. Let's use R2 again. So now what we have to do is we have to see if the loop should continue at this point. I'm being very careful here, by the way. R0 and R1, I cannot mess up. So I have to be very careful with R0 and R1. The other registers, I can sort of reuse them locally, but R0 and R1 need to be left alone. They're very important. R0 is the array address, and R1 is the current minimum value. So I have to make sure that I'm careful with those. The others I can reuse a little bit. So again, it's assembly, so I increment the offset, and then I need to get that value to see if the loop should continue at this point. So I have the offset variable, then I need to get the array length. So let's see, I can use R4 here. So this is, it's ugly looking, but I'm writing it like I would kind of in a high level language. The array length variable tells me how many elements. I know it's 10. So the offset is going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, just like I would. This is sitting at 10, so I'm going to get that value, load her up into, so R3 is I, R5 is the length of the array. I'm going to use a test equal this time. So I had to think a little bit. We could use a compare here, but I'm just waiting until I reaches the length. So I is going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So at some point R3I is going to become 10, which is what R5 is. So when I reaches 10, we need the loop to break. But as long as it hasn't, then we can branch back to the for min loop. Let me make those look a little bit nicer. I think that's all right. So continue the loop. So there's the whole for loop in assembly. Here's the for I equals 1. Here is the I less than or not equal to the length of the array. Here's the I plus plus. So it's kind of been all over the place, but I tried to label it up so that you would know what pieces meant what for the loop. So there's the whole loop. As long as R3, which is I, has not reached R5, which is the length of the array, then it's safe to continue the loop. And we'll just grab the next value and keep going. So if we get here, the loop has ended. So once we get down to this line, it's because we didn't branch, meaning that I is now the length of the array. So at the end of the array, at the end of the loop rather, we have to store that value back. So once we get here, we know R1 should be the minimum value in the array. So I can do some reusing at this point. I don't need the array itself anymore. So I'm going to grab, what's it called? The minimum variable. So once the loop is done, I can take R1 and put it in this variable. So there it is, where I store R1 back. Now that was kind of a hairy bit of code to write. I had my fingers crossed that I didn't leave anything out. I think I didn't. We're going to find out here in a second when we run the compiler, but that is a pretty intimidating piece of code. I need to... That's all of it. This is all of the code, less the push and pop, which I'm going to add right now. I used all the way through R5. So R0 through R5, and I'm going to pop R0 through R5. So the whole code for find minimum is sitting there on the screen. I'm going to go hit it with the compiler and see what happens. Miracle. Hopefully yours is compiling. I'm going to go ahead and apply the remaining steps and see if it runs. So I'm going to do the elf part. I'm going to do the bin part. And then the st flash part. I'm hoping for a jolly good, which I did. So I'm going to show you my camera. It's not doing anything, which may or may not be a good sign. I don't know. I feel like it's not a good sign. It does compile though, so I'm pleased with that, but I feel like it's not a good sign that nothing's happening. Unless it's stuck in a loop somewhere. It can entirely be that it's stuck in a loop. Increment offset. seems all right. Clear bits, display mode. Mode 0. The mode started in 0. It should have been displaying all the values. So I have a feeling I might have a bad loop. So here's what I'm going to do. I'm going to comment these out for now. I'm going to comment out the code that I think is objectionable possibly, and then I'm going to go back through and do all the steps just to make sure that it's doing mode 0 correctly before my code messes it up. Okay, that's jolly good. No, mine doesn't even display, so it's not any of that. What did I break? I have a feeling I broke something. I don't know if you guys are having any different mileage than I am, but my code just does not run, which is a concern. It may have something to do with the no, I think that all stayed the same. So I don't know if anyone's having any different mileage than I am, but right now mine doesn't do anything. Unless I am in the wrong folder or in the wrong folder. No. Clear bits, display mode. Mine does nothing right now. So, alright, Jax is dead also. So, what has killed it? One wonders. What has killed it? Config, macros. Table reset handler should be alright. Pin handlers should be fine. Configure interrupts, configure GPIO. Those things didn't change. Main loop. Display. Hold on a second. I know what it is. The array isn't populated. What does macros want to... The array is all zeros right now. All right, huge deal. Populate the array. My guess is that it's showing all zeros. So I'm going to leave it sitting on that spot for a second. Populate your array. 2, 3, 4. I got to reassemble, re-elf, re-bin, re-flash. Okay. No. At least not for me, it didn't. But it wasn't being populated, it's true. Oh, now Jack's works. Well, why doesn't mine work? Populate array numbers. All right. Recompile. Re-elf. Re-bin. Re-flash. Well, mine's just dead anymore. Now, I was messing around with it to try to mine my circuit to try to compile an old lab for somebody. Mine's dead. Whose works? Darn it. Well, Vince's does. Jack's works. You can try putting in the min again. I mean, Max just doesn't do anything, so that should be fine to comment all those in. Mine just doesn't work anymore. Now, I did plug in some stuff this morning, which possibly I screwed something up with that. But I don't feel like that should matter. Well, let me just remove it. Yeah, my board doesn't do squadoosh. Anybody else got it to work? Populate array var, increment mode, decrement mode. Those things shouldn't even matter. Mine don't do anything. What are we in mode 0 to start? Yeah. Mode 0 should be cycling the array. Right here, it should be cycling through the array, except for it's not for me. The only thing I can think is that maybe I lost a wire or something. Like if I'm not grounded anymore, that could be a problem. But I'm not seeing it. Anybody else? Okay, exactly. It's working. Yeah, it's, I mean, my assumption is it's my board, which I'm gonna disconnect and repower. Just checking stuff. I did fiddle around with my circuit this morning because someone sent in a late lab and I was trying to make it run. But I don't imagine that's the issue. Well, if yours is working, you're good to go for now. If it's not, you can stick around. I'm going to stay on stream and try to get mine to work and then say what it is that made it work. But right now, mine doesn't do anything, and there's people who have the same code that do have it working. Make sure I'm in the right folder. So I'm checking things like, am I working on the right files? Am I in the correct folder when I'm running the compiler, all that stuff, and I am. Config it in touch. Main, I'm going to comment out a thing and just see 2, 3, 4, 5. Yeah, it just doesn't do anything. Populate array, display mode, display array, I think just works. Yeah. Display offset, that's interesting. Why would I do that? Oh, I know why. Reset offset. Display array, I do reset the offset. Well, I don't know, you guys. If you are working though, you just call it a day. If you'd like to. I'm gonna sit here. I don't have that long to sit here. And try to figure out where I went wrong. I've commented out compute min just to make sure that that's not a problem. But compute max doesn't have anything, so it should be fine. Compute average, decrement mode, increment mode, populate the array. I am doing that. I'm just going to go do a couple of experiments and just see, like I'm going to change the mode to be mode 3 instead. And see if that changes anything. I'm going to sit here for about 15 more minutes and then I'll have to tell you next time that's I did the wrong order of things. So. Okay, so when I change the mode, that does work. So interestingly, yeah, I broke a button. I'm pretty sure that I broke a button somehow. I found it. I think no, it does. That's 5 volts, right? Goes to 5 volts. It does. All right, that wasn't it. I thought I found the problem with the button. I'm worried about this button having broken something, so I'm going to take out what I did with that earlier. Okay, for me, I have a broken button. Or something. I cannot get this button to work anymore. Where it says there's a problem. Okay, so to trace a syntax error, if you're getting a line number in main, then you go to that line in main, and if it's a call to a macro, then you have to go to the macro and look in the macro as to how to trace that. Something's broken about my whole circuit right now. If yours is working, I am envious of you because mine is not working. I can get it to show mode 3, and then I can go down. Wait, increment mode, can I go back up? Okay, that's 3, 2, 1. 2, 3, 2, 1. Okay, wait, that's 0. And then it doesn't come back up anymore. Increment mode, decrement mode. You guys have the same code that I do, and I feel like increment mode or decrement mode. R1. If R1 is lower than 3, I can add to it, store it back. If R1 is higher than 1, I can subtract from it, store it back. It'll do mode 3, and then I can go to mode 2, and then mode 1, and then mode 0, and for me mode 0 is broke. Display array, numbers length, offset. All right, compute. I'm going to do min is, I'm going to put it in mode 1 and see if it shows a 1. Doesn't show a 1. Okay. So mine's broke. I need time to fix it. I think it's something with my circuit because some people have the code working. So anyway, we're going to leave it right there. We got through the homework, and we will, on Thursday, we don't have that much code left to write, so on Thursday we will come back and we will, I will let you know what I discovered about what's broken on mine, and then hopefully I will help you get yours fixed. Worst comes to worst, we still have Tuesday next week, and we will get our stuff working. So anyway, sorry for the trouble. I don't see anything wrong anywhere, so I'm gonna go figure that out. And then share with you. I'm just gonna check the orders of some things. I'm sort of suspicious. Numbers length offset max min, numbers length offset average, numbers length offset min. Okay, no, all that stuff is okay. Anyway, I will keep track of what it is that I'm doing to fix things, and hopefully it's something simple and stupid. But if yours is working, then feel good about that. If it's not, we will get it working on Thursday. We'll come in straight off and get it fixed. I did fiddle with my wiring a little bit this morning to try to grade an old submission of somebody, so I may have messed myself up there. So anyway, we'll relax about it. We will all do our best, and I'm not going to ask any more of you than I can achieve. So we'll be back on Thursday, and we will get this thing working. I suspect that I've done something simple and dumb. And once I figure that out, then we'll fix it. So today's Tuesday. I will be here on tomorrow. You guys probably usually don't need that anyway. Thursday at 8:30, we'll be back. You too, Vince. Thank you. We will do our best. I'm sure it's something simple and stupid, and I will fix it, and we'll be all good to go again. So see you guys on Thursday.